and thank you for coming to my talk today. My name is Jeremy Eder. I work in the performance engineering group at Red Hat. I'm the co-team lead for performance and scale of containers. You may have seen me from some hits in the past, or supposed hits in the past, working in the low latency area, and in RHEL, basically, working on RHEL performance tuning. So I try and use all of that knowledge and bring it forward into the new toy/tool realm that we're in now. Today's talk is about container performance. What you saw scrolling through before is a list of my friends and coworkers that help Red Hat quantify, test, stress, break the container stack so that you guys don't run into any of that crap. And as all of our teachings or learnings, our goal is for all of that stuff to end up in the product such that you don't need to worry. When you purchase something from Red Hat, you'll get all of our teachings, or as many as we possibly can, in the product. And of course, as open source, you can go ahead and change all of that stuff if it doesn't suit you. So the idea is to provide some sort of value on top of what the community provides, whether it's integration and testing, and I'm going to show you some test stuff in a few minutes, and as well as the performance and scale. So with that, let's see if I can figure out this thing. Cool. OK. So that's me on Twitter. I find, my wife says I spend too much time there. But I find it's like the easiest way to ingest huge amounts of information as quickly as possible. Anyway. So what we're going to talk about today is, again, this is an overview of what we're doing. And if you guys read the abstract for this talk, it talks about how we're applying a DevOps model. I'll try and explain to you how you might apply that in your own area of your company if you're not already doing it. Lay some of the foundation for the rest of the talk. I've got more data than we can ever get through. So I'll probably zip through some of it. But again, all the slides and stuff is going to be available for you. And it looks like there's a camera in the room, so probably be recording unless I forgot to put the film in there or something. I want to share with you guys how we run our tests so that you can run them as well, same ones we run. And we're contributing some stuff upstream. We've got some stuff in OpenShift. It's a work in progress, but you can go ahead and clone that, and I'll show you where it's at later in the talk. And then finally, who saw the OpenShift demo yesterday with the almost Fruit Ninja thing? Was that cool? I thought it was pretty cool. I don't know if you noticed, but when the camera panned behind Jason DeTiberis, there was a Grafana screen. Our group sort of kind of helped with the monitoring of the infrastructure that went behind that demo. And I think it pulled it off pretty well. I thought it was cool. Actually, funny story. A remote person texted me afterwards and said, I won one of those awards. Or like, I was one of the top 10. You need to pick up a T-shirt for me. But I can't find where that T-shirt needs to be picked up. So apologies to Joe. OK, so that's what we're going to go through. Now, has anybody been to an OpenShift talk at the summit today? OK, so this slide is clearly not done by an engineer because it's way too pretty, right? So I borrow it because it describes the OpenShift topology at a high level. And when, as a test architect or performance architect, this is what I need to know when I'm going to build up a list of stuff to look at. So, and I apologize if you can't see it in the back. I tried to make it work for the people in the back. But there is now a red arrow next to API and authentication. So we have tests for basically all of these little blocks. The authentication layer, certainly the API server, which is a critical piece of, it's basically the way that clients instruct the scheduler to do anything. We got the data store, which in OpenShift is etcd. The scheduler, as I already mentioned, Kubernetes is this core container scheduler for the distributed system. We've got management and replication scenarios. We've got what else? Tests for the nodes. Some folks on our team are ensuring that we can get some really good density on each node. So there's some tests around that. Of course, the routing layer. I'm going to show you a really short demo at the end about testing, how we test the routing layer. quickly how it works is there's either a hardware load balancer or an HA proxy, and that is what is called the routing tier in OpenShift. So also persistent storage, right? Red Hat has acquired Inktank and Gluster over the years. We've got a great software-defined storage story. All those engineers are working to incorporate software-defined storage into our container platform. And it doesn't necessarily even have to be those two technologies. The demo I'm going to show you today is on AWS and uses EBS volumes, dynamically provisioned EBS volumes. Really hot. I'd like to thank Steve Watt for making that work. And of course, it's got a registry in it, right? The Docker registry. So these are all hosted as containers on OpenShift. So you've got, in addition to that, actually, there's little oversight on my part. There's no metrics or logging on here. Two other things for OpenShift. We've got Hawkular-based metrics that tell you what every container is doing, and then we've got logging for every container that gets shoved into Elasticsearch. So we also have tests for those. Okay, so we're trying to cover every possible scenario here, and I've actually got a laundry list of stuff we want to do. We want to do a chaos monkey, chaos with a K, or go in there and just snipe nodes or snipe PIDs or whatever, cause havoc inside the system and figure out how the scheduler responds. Someone says they want 1 second of downtime if a pod goes down. That's tough without false positives, but I think we can get as responsive as we can probably do fairly well. 1 second is tough, man. Okay, so if you've been to any of my talks, I cannot possibly do it without talking about TuneD, which is a tuning profile delivery mechanism for RHEL. It's on by default in RHEL 7. And what it does is take a bunch of syscontrols and power management stuff and bake it into the operating system such that you don't have to worry about that stuff. You'll get a data center-centric operating system. It's not something you would install in the server variant. It's not something you would put on a laptop because these tunings don't necessarily suit a laptop or an interactive workstation. Therefore, data center operating systems. So we have, 8, 9 something profiles right now, and that are shipped with base RHEL. There's a concept of inheritance. The default right now is called throughput-performance, which is the top left. So if you install RHEL and you do tuned-adm active, it will tell you you're running throughput-performance profile. So, and those can easily be shut off or changed, whatever. The point is that from a performance standpoint, you're always in a throughput versus interactivity or latency balancing act, and you need to tune the system for your workloads, and there's no one set of tunings that will work. So we decided to encompass all of our team's work into these profiles. You can select them with just one command. We've got them all over the ecosystem within Red Hat now. We've got new profiles for NFV, which you'll see in a talk this afternoon with some other coworkers from the performance team. We'll show you some of the guts of how we're doing just a ton of tiny little packets and incredible latencies. And of course, we've got them for OpenShift. So what those do is help mainly, in OpenShift's sense, basically, it uses throughput performance and adds on some stuff to help with density. And as we learn more, we're going to incorporate it into those profiles. When you guys update your systems and patch TuneD, you'll get the new settings automatically. Some of the examples of what performance can do here, this is a system that has nothing untuned. An untuned system, and you run an FIO test, right? If you're familiar with the FIO benchmark. And then all you do is enable TuneD, and it's like twice as fast, or 73% faster if you're splitting hairs. And so that's an example of good. It's never worse. It's always better, but it's not always 73% better. So anyway, here we are with an example of why TuneD exists. I mentioned, or as the slides were scrolling, you probably saw a couple of guys in there that had storage on their name. Those are guys who have been working on Gluster or Ceph for several years, and they have domain knowledge in that space. And they've picked up on the container part of it, and now we're running containerized tests, hyperconverged tests on any public cloud, bare metal, VMs, OpenStack, the whole mess. So we've got all of the testing automated for that, and providing feedback to white papers that we've published as to how to configure your system for top performance, and what to do and what not to do, kind of. So on with the data. We have Gluster running inside OpenShift 3.2 and 500 pods. A pod is a group of related containers in Kubernetes speak. 500 pods running on 5 nodes, shoving as much storage traffic through there as possible. And we see here, if you see how 25 is the highest one, who can guess how many CPUs were in that system? 24. So basically, that system was CPU saturated, and that's why you see degradation after that, which makes perfect sense. There's no more CPU, you can't go any faster. Similar data from Sysbench, which is it has an OLTP mode and then like a calculate primes mode for CPU type benchmarking. What we're trying to do here is show that we've got you've got bare metal performance and you've got containerized performance, and they're within the same ballpark. And then the blue line is when you start talking about hyperconverged. So we've got the Gluster daemons inside pods on the same system that the benchmarks are running on. So in that case, the reduction has nothing to do with the apps themselves. It's just that there's less CPU to go around because you're packing more work onto one system. So that's a hyperconverged scenario, and that's what you can expect if you were to do something like that. We did some testing on EBS and bare metal and Ceph, and I mean, it's just endless the amount of permutations we went through. The good news is that we can saturate an EBS volume with Ceph inside a pod, no issues. My idea here is to run at the speed of metal, always. In the case of EC2, you're subject to whatever the heck that cloud provider wants to do, whatever any particular cloud provider wants to do. My point is that if I'm on bare metal, I get a certain throughput. If I'm on a cloud, I get a certain throughput. They should be close. In this case, they're damn close, so it's a really good test scenario for us there as well. Storage aside, I'll show you again in the demo. I'm going to show you it's got some EBS components to it, so it's pretty cool. And the way it's so damn easy. It's a joke how this stuff gets wired together in the product. We also did some network testing, of course, throughput and latency testing. Did it on bare metal, did it on EC2, did it in a bunch of different variations in EC2 like SRILV, and they call it enhanced networking. The idea here is because OpenShift.com, which recently launched in developer preview for the OpenShift 3, which is the Docker and Kubernetes part of it, just recently launched in a developer preview. So we were specifically targeting, as everybody knows, or you may not know, it's hosted on AWS. It always has been for the since we launched the product. So we wanted to make sure that AWS is first-class citizen along with OpenStack as well, and along with bare metal, of course. So we've got a scenario here where lower is better. You see, this is latency in microseconds for a full round trip for 2 TCP streams of 64-byte packets at the same time into pods on bare metal versus into pods on EC2. And you can see they're within handfuls of microseconds of each other. Most people won't ever care about that couple of microseconds, especially in a website scenario. You're usually talking about milliseconds for web page interactivity, not microseconds. In terms of throughput, you can get close to 10 gigs on EC2. They've got some tricks around something called placement groups. Has anyone ever heard of a placement group on EC2? Yeah. If you use those, you get like a better chance of the VMs being on the same top of rack switch or something where they're physically located nearer to each other, and you'll get better performance out of it. So there's some tricks to each cloud provider into getting better performance that the operating system won't be able to help you with until the substrate that you're working with is configured correctly or configured for more performance. And placement groups is one way of doing that. So got another couple of guys that are working on the web console. When we go to launch OpenShift, we want to make sure it doesn't fall over on day one. Right? That would be bad. And so they crush the web console with users. We've got a tool called Cluster Loader, which will it's part of our repository, and what it'll do is create as many users as you want, create as many projects as you want, create as many pods, replication controllers, routes, the whole mess, and all together, as well as how many persistent volumes. So the whole stack can be loaded from one YAML file. It's pretty cool. I'll show it to you in a minute. So basically what we have to do is we have to load the environment as phase 1, and we have to test the environment as phase 2. So the loader is part 1 of it, and then we've got workload generators, basically JMeter stuff wired together with some usability improvements, because JMeter is, I don't know, does anyone use JMeter? I mean, the XML is atrocious. So it's really not human usable in its current state, at least for mere mortals like myself. So anyway, these are response times. They're still in the dozens of milliseconds for page loads, which if you've read any of the documentation on it, somewhere in the high 100s to 200 milliseconds is what the human eye can perceive. So we're in good shape. Another cool feature of OpenShift, so this is an application actually under load, and there's something called horizontal pod auto-scaling in OpenShift. And what it'll do is if you have an application, the system will detect when load is high, and it will automatically add additional pods to the replication controller. Replication controller could start with a value of 1, and then you keep adding them until your performance is acceptable. And that's what's been done in this scenario here, where we've got 300 millisecond page load time with one pod, and then the additional pods were added to the system, and as you can see, the page load time went down. There's a point of diminishing returns where it's not going to get much faster than 50 milliseconds just based on the fact that it's on a cloud provider and there's network connectivity to worry about, et cetera. The point here is that you can automatically add additional infrastructure, and the scheduler will take care of that for you. So I forgot to ask for questions. The gentleman had his hand up. It doesn't. It says there's no time anywhere on this graph other than the y-axis being page load time. So actually, this is a good question. The kubelet itself has a lot of tunables in it about how fast it reacts to situations. I mentioned earlier someone wanted 1 second response time for an application. There's tunings that can go, like how quickly do we evict a bad node? How quickly do we reschedule pods? These are like site-specific tunings. So it does not account for that, but there's tunings that can shorten those times, is my point. If you want a node to be evicted from the cluster within 1 minute, you have to configure the cluster to do that. If anyone's ever used Red Hat Cluster Suite, there's several similar or analogous policies, or any clustering software, analogous policies that attempt to reduce or eliminate false positive evictions at the cost of how fast the system reacts. This is a classic scheduler problem. So. Point here about horizontal pod auto-scaling is hands-off. So I mentioned a white paper earlier, and in there is some capacity planning. We're going to rev that white paper for the next release. It'll be revved with every release of OpenShift as new stuff is introduced. And one of the areas that we're focusing on is capacity planning. So the question is, how much memory do you need? How much CPU do you need? How much disk do you need? And of course, how many machines do you need? We've got some formulas in the white paper, and there'll be more formulas in the future. In this case, what we have, just as a real simple example, is that certain languages have a different footprint. Everybody knows that Java grabs all of its memory up front. Everybody knows that PHP is fairly light. Nginx is even lighter. Those sorts of things where a scenario where you're not under load doesn't give you a good calculation. So that's why these web load generators come in, where you can say, okay, by default, in a steady state, my whole system is consuming 500 gigs of RAM, whatever the number is. But when it's under load, it's 3 times that. These are things that fit in, that are missing variables in a capacity planning formula that you'll need to fill in based on your site-specific config. So this is just some data where we're not even blasting it. It's only 100 transactions a second based on different frameworks. Those apps are available in the OpenShift GitHub repository. You can load them up yourself. So we use all of those the examples that are in OpenShift's GitHub are what we're using in all of these tests. Another thing about capacity planning. So the metric stuff persists all of its data to Cassandra, which is an in-memory database, and then eventually gets persisted to disk. Something that we're investigating currently, I figured I would give you some kind of active investigation stuff, is if anyone's familiar with the VM dirty ratios in the kernel, based on how much dirty memory you have, the kernel will decide to trigger a write back, and that will it will write stuff to disk. Cassandra's got the same policy, where it will over time persist things. And so we've got this sawtooth graph up here, which I know is hard to see in the back. I apologize. But there's a sawtooth graph where it's it's accumulating metrics, and it's persisting it, it's accumulating, it's persisting it. Part of what we're going to do for 3.3 is nail that down so it's a little bit more steady. We find out when we start shooting a bunch of I/O down that it will block CPUs, and other processes won't be able to get won't be able to get scheduled. It'll affect interactivity. These are the types of things that this sawtooth scenario can create. So we're going to try and smooth that out. Also, offer some tunings that you can configure how much data you want. So One of the things we're finding is at a tremendous scale, the defaults might not make sense. We just have too much metrics coming in. If anyone's ever operated a distributed system, familiar with how an RRD works, where it expires old data as time goes on, that's exactly the scenario we're going to work to achieve with this metric solution. Some more work is going on. So we have team members who work in upstream Kubernetes, as you can imagine, to improve scalability and performance of the control plane. This graph is about something called the pod lifecycle event generator. So we had this situation in the early versions of Kubernetes where Kubernetes would talk to the Docker daemon a lot. It was very chatty. There's no caching. It made perfect sense to instead of use a polling mechanism to talk to Docker across however many nodes, to move it to an event-driven model. And so we've done that upstream along with a tremendous amount of help from, of course, from the Google people to implement this. And so instead of 3 cores to run 250 pods, 120 pods, we're down to a quarter of one pod, not even 10% of one core. So the efficiencies efficiency improvements are tremendous, and all of this code is already GA. So if you installed OpenShift in version 3.1, you'll see these efficiency gains when you upgrade to the next version. And we've got more, a lot more efficiency improvements as we approach the thousands of nodes scale. We have a lot more work to do, and in fact, I have a slide on how we're going to achieve that in a couple of minutes, I guess. Part of the problem, oh, actually, it's right up here. So part of the problem is actually that the nodes talk to the masters, the API servers, a lot. And they're fairly chatty. It's basically a fairly chatty protocol. We want to reduce that. And what we're looking at is a graph here of the number of sockets that get open on the API server. So this is this will be a limit if we don't address it. The good news is we've already addressed it, and along with many other bottlenecks. So if anyone's familiar with like the network path through the kernel, the session setup and teardown phase is expensive. It's made even more expensive in OpenShift because all this stuff is encrypted, as well as the fact that Golang has a fairly inefficient TLS mechanism in it. It's kind of CPU hungry. So not only is there a lot of open sockets, but there's a fair amount of CPU use associated with it that we just want to get rid of. So, all this socket setup and teardown is a lot of unnecessary churn and work on the system. It also causes network traffic. The whole thing is just, in its old state, it was doing this. This is at very wide scale. So you wouldn't see this on anything like in the hundreds of nodes range. Once you get beyond that, which we're doing, you have to worry about these sort of scenarios. And so we have a couple of things in the hopper and these are all along with the community, sort of Red Hat. I would say Red Hat participates in these and leads some and doesn't lead others. But some of the key things are around etcd3. I think the two main things there are that it does incremental snapshots. Instead of dumping the whole memory to disk, it does it over time. And it also increases the scalability by at least a factor of 10. If you've ever seen a presentation on from CoreOS on etcd3, you'll know that they're very intent to get this thing into the product. So in 1.3, we've got it working, and we expect to transition this thing to full support as tests prove out that it's viable. The second piece I mentioned earlier about all of those sockets, right? We've enabled or we've added support for HTTP2 protocol, which will allow us to reuse existing sessions and get those numbers down from the 20,000 range into the couple thousand range, or even the idea here is to get it to like 1 or 2 sessions per node and have all the comms go back and forth on that handful of sessions. That's about as lightweight as we can make it. So that's off by default in Cube 1.3, which I actually forget if it's even been released. If it hasn't, it'll be very, very soon. But that's off by default. Our team did the enablement on it. Tim Sinclair did the enablement on this one. And off by default, and you can actually enable it on an upcoming version of OpenShift. So these are not things you need at even reasonable scale. And even at big scale, these are things you can deal with as long as you just understand that you're going to pay CPU for these things. The last part is a very common question that I get is, how many pods can I put on a node? It's actually not the right question to be asking. The right question to be asking is, what is your workload? The number of pods doesn't affect things the way you think it does. There's very little overhead to individual pods. We know this because our tests prove it out. We have a little binary called hello OpenShift, which all it does is open a TCP port. It's a Golang binary, and it's all it does. And we put that guy inside of a pod and scale it out to thousands and thousands and thousands of pods, and it's fine. Things are fine with it. But it doesn't use any memory or really any resources. So if you have an application that's very heavy, if you have an application that asks for 8 gigs of RAM, let's say your JVM is 8 gigs, heap size. How much memory do you have on your system? To me, it's simple math. You have a 64 gig system, you can fit 7 of them on there. You got to leave some room for the OS, right? Number of pods doesn't matter. So unless you're hosting or testing these useless little apps that just kind of turn on and hold themselves open, the number of pods doesn't come up as often as you think. So in OpenShift 3, we had 40 pods on each node. In OpenShift 3.1, we're at 110. And in OpenShift 3.3, what we've gotten upstream, Rob Ratai very recently has written a patch that allows us to move this to an algorithm that says you can run 10 pods per core. If you have a lot of cores, you can run up to 250. So if you have large systems, you can get from 40 to 110 to 250, and we're going to keep progressing. Actually, we've laid the groundwork on the IP address management side so that in OpenShift 3.3, you'll be able to have 500 pods on every node. And these, by the way, these are all just like what comes out of the box. Folks can always tune these things. But this is what we're validating, and it's like this is the supported with a capital S kind of scenarios as we get further along in the product. So this is kind of a screenshot of what you might, probably no one saw it except me because I was looking for it. But what Jason had on one of those monitors was this Grafana graph. And what this is CollectD feeding into Graphite, which is visualized through Grafana. And we've built this dashboard that helps us understand an OpenShift cluster. So it's got all the normal 4 food groups, CPU, memory, disk, and network. And then it's got things like how much memory does each daemon use, how much CPU does each daemon use. And we've got some sort of more cutting-edge stuff that tabulates statistics from the API server itself, how many etcd watches are open, how many etcd queries, gets, sets, fails on etcd. So we've got a tremendous amount of diagnostics in there, and the idea is to learn as much as we possibly can from our testing, as well as from the developer preview of OpenShift.com. As part of the reason we're doing in developer preview is that we can have a controlled environment of a certain size that has no business SLA on it. And we have all this additional metrics on it and people watching and observing the users on the system. What are they doing? Are they breaking things? How can we fix that? How much headroom do we have, or sizing, et cetera, et cetera. So we have all of this monitoring in place in order to enable that stuff. So I mentioned earlier that we have our tests in 2 places. The first place is on GitHub over here. And the second place is upstream in Kubernetes in something called the E2E tests, end-to-end tests. At the moment, those are mostly functional. We're extending them. Google is, of course, extending them at a tremendous velocity. So we've got our QE team. Everybody contributes to the repositories where it makes sense. In this case, if you clone that thing, which you can do right now, you'll see what we have is on the left. I had mentioned earlier the chaos with a K-monkey. It's a plan, something to do. Logging and metrics tests are underway. Like, you'll see PRs for those in the next couple days, most likely, to be pushed upstream into the SVT repository. We want to do more complicated scenarios, and this will make more sense when I show you the YAML that describes the cluster loader. But basically, we're going to ship a bunch of different scenarios. We're going to commit a bunch of different examples to the repository and basically say, for 100 nodes, this is the set of tests we do. For 5,000 nodes, this is the set we're going to try and do, that sort of thing. Further, one cool part of working at Red Hat is that you can see exactly what we're working on. So our backlog is managed on Trello, as well as the rest of the Atomic and OpenShift program. Trello.com/AtomicOpenShift, you'll see everybody's board. In this case, this super easy to remember URL is the Scalability and Performance Teams board. And on there, you'll see our backlog. You'll see spike shedding on various, how the hell do we do certain things. And it's really great to be able to have that visible to our customers so we can have an informed discussion about the order of operations. We want to do the things that are most important first. If you're in a lot of debt, you don't pay off the little, tiny little credit card. You burn down the big ones first. So this is technical debt. It's a good thing because the product is gaining in popularity. We also know there's, it's new technology, and there's a lot of research and development needs to be done. So that board, you can hit it right now and check out all of our upcoming projects. I mentioned the Kubernetes tests, right? We actually ship them in OpenShift now. If you were to do those commands, you would get the tests. The bottom command is how to run the test. It will take an hour, depending on the size of the cluster and compute power. And it will validate your environment. There's some work to be done there. So actually, I don't think we're fully green on those tests at the moment. But a lot of the tests that are upstream actually do not apply to OpenShift. So it's not that things are broken. It's that our design decisions maybe diverged a little bit, and those tests no longer are valid for OpenShift. So anyway, that's how you run those conformance tests. And there's a couple of different focuses. I love this syntax with the Ginkgo focus thing. And you can run, there's a density one that seems to be very popular internally on our team to stand up a whole bunch of pods and stuff like that. So, okay. Anyway, back to, so sort of come full circle. You've seen most of the test data. Here we are back at the environment. Let's figure out how to test this thing. I've got a fairly simple environment stood up. 4 nodes on EC2. One of them is the master. And normally, again, this is a test scenario. Normally you want multiple masters, of course, multiple routers, multiple registries, and of course, many, many nodes. But for the purpose of the demo, let's assume we're just in like a POC phase. We've got this master, an infrastructure machine, which runs the routers and proxy I mentioned earlier, and which is called a router. And then I've got 2 nodes that host the pods or applications that I'll be running. Some of the things you'll see in the demo are a tool called BZT, which is from the BlazeMeter guys. If you haven't seen BlazeMeter, they make a lot of fun tooling around JMeter. Quick pop for them. They make a really great open source product, which is free to use. And it wraps JMeter in something that's actually legible by human beings. I had mentioned we're feeding data into these graphite systems and visualizing them with Grafana. And the way that that data gets transported is collect D. So let me see if I can show you a couple of things. Can the guys at the back see it? Okay. The cluster loader is a Python script. It talks to the API. It talks to OpenShift via the command line client currently. And it will instruct it to do certain things. So the same way that BlazeMeter makes JMeter consumable, this makes loading up a cluster consumable. The idea here was to be able to describe a very complex environment in a human-readable way and say, allow for different scenarios based on these configuration files, right? So in this case, super simple demo. What I've got is one project that's the cake PHP in MySQL example. If you go to GitHub OpenShift examples, you'll see all this stuff. And so there I got a PHP example that's got a backend database, which is on a persistent volume. Since I'm on EC2, this will be an EBS volume. And I've got the same thing going through with all the other examples that are in OpenShift. So we've actually customized these because some of them don't have persistent volumes, but I figured for this test, let's do the whole shooting match and include the persistent volume in some of these things. So these are full-blown applications that would represent what a user wants to load onto OpenShift currently, a full stack, multiple pods talking to each other, okay, with load balancer, with persistent storage. I'm not cheating in any way right here, so it's a complicated scenario. It goes through, I got Django and Postgres, Node.js, and MongoDB, okay? Also, there's a JBoss 1. And I know there's a JBoss 1 in there because there's always one pod that takes a little bit longer than the rest to start. So I've also got Tomcat and Mongo. But the point is just that this is a nice variety of stuff, right? At the bottom, we built this thing that allows us to ramp up load gradually over time, or blast based on how the config is. How big it does steps each. Like let's say it loads 100 pods at the same time, then it moves on to the next group. After 100 pods are started, it moves over to the next group. So that sort of thing. So we can watch the resource utilization on those dashboards and say, we got to the 100,000th pod and we crashed and burned, something like that. So we can say to the capacity plan folks that are documenting on capacity planning, if you have a scenario with these variables, we're comfortable at these load levels. If you go here, there's dragons, et cetera. Okay. And then, of course, in each individual step, we might decide to rate limit it for 100 milliseconds or not. So basically, we've variabilized all of these things and put intervals everywhere such that we can have a very flexible and easy to express framework for running these tests. Okay, so that's all that is. Oops. So I'll take you over to the web interface for OpenShift. I'm sure you've seen this guy before. I've got nothing in here now. These are the ones that come with the product. Inside these guys are the metrics pods, the router pods, logging pods, infrastructure pods, hence the name, OpenShift Infra. If you try to delete these, luckily you can't, because things will be spectacularly broken if you try to do that. So anyway, this is what the web interface looks like. And for me, I don't really particularly care, but I just wanted to show you that we've got this thing. It's a web interface. For me, I'm mostly talking to the API server, and for the rest of our guys on our team, almost never look at this, but we do need to test it, and I showed you some data earlier. So anyway, so we've got nothing in there, right? So come back to my terminal, and I showed you the config that we're about to load onto the system. I'm just going to run Python cluster loader, give it the Summit config, and we're going to load up those, 6 or 7 pods, something like that. So it's going to go ahead and do that. At the same time, it's currently CLI. We'll move it. We'll move it to the API. Actually, as with most toys to become tools, it's an evolution. So. And a lot of this may actually end up getting upstreamed into Kubernetes. We're not really sure if we actually deal with, so Kubernetes has these special interest groups, and it's this public forum, which if you're interested in Kubernetes, I would suggest you join. There's plenty of customers that contribute. And we interact with the Google guys in that format, and we decide what tests belong where and why, and what they're interested in, what they're not interested in, that sort of thing. So anyway, we got all of this stuff. So it exits before everything is totally stood up, but so we can go check if it is stood up. Okay, so all of those pods are up and running now. If I go back to the web console and find my mouse, you can see we've got a lot of projects in here now. So this is the same system that I just ran all of those scripts on. Okay. Click on an individual. So a project is like a tenant. It's, if you're familiar with the OpenStack vernacular, a tenant is the same as a project, is the same as a namespace. Not the kernel namespace, the Kubernetes namespace. So the vernacular and like context is important here. Segregates users from each other. In essence, it's like just a couple of bits of etcd schema that keep people separated, as well as, in the case of OpenShift, open flow rules. I didn't go into the details of the way our SDN works, but it's open vSwitch, and we use open flow rules to segregate traffic from tenants. It's on by default. You can opt out of that sort of thing if it doesn't make sense for you. It's also based on VXLAN. So we've got all of these apps running in here, and if I click on this guy, I get the example application. That's it. PHP app talking to MySQL. That's it. So anyway, point is that it's up and running. So to a person who's interested in testing the system, it may not seem like I can tell it's not very impressive, but to me, knowing what's actually going on and to get to this point, this is where things get cool. I'm showing you a fairly simple demo where we've got only 8 apps. Imagine if we have thousands of nodes with many tens of thousands of applications. This is a front end. So the YAML here, I just change that number 1 to 10,000 and run it again. That's it. So the idea here is that framework is very flexible. So let me take you over to the Grafana dashboard at this point. And I know I'm running out of time. But I'll take, so this is the Grafana dashboard, which is collecting data from the cluster that I just loaded up. So you can see a couple of minutes ago, we got some CPU spikes, right? Those are containers launching. And since there's no load on them, you get all that CPU back after the containers are created. Now we're in an idle state. The memory, however, you don't get back because the application has got hold of it. Okay? Most of it is in the Java container, since you asked. And then on the bottom, we've got a little bit of network traffic, right? Those are the pods getting scheduled and all the chit-chat that goes on to get these things scheduled. In this case, difficult to see from where most folks are sitting, but it's in like the 4 or 5 megabit range, and it lasts just a second or two, and then we calm back down, and now we're in a steady state. Remember I showed you guys the graph of the apps that like PHP had like 10 megs of RAM, but you put it under load and it's up to like 60? This isn't the unloaded scenario, and that graph was the blue bars. So if we can put some load on it, and I'm not quite sure how this is going to look, but let's see. What the heck did I call it? EZT Summit. Oh, let me show you this file first. So I mentioned earlier that BlazeMeter has a command line utility that drives JMeter, pip install BZT, sucks everything down. And what I've configured the scenario in this, so this is a load generator profile. In this scenario, I'm just going to do 10 connections and hold it for a minute. So there'll be 10 simultaneous connections. When the first one ends, there'll be a new one. It will attempt to keep that at 10 active connections. There's 100 milliseconds in between each hit. It's going to hit just this one URL, which is one of the example applications I stood up. Okay, and it's going to spit out some stats, which are not important really for here because this is a totally untuned environment, contrary to the subject matter of this talk, right? So it's in public cloud on small nodes because I had to pay for this out of my kids' college fund. So okay. Let me get it to the top of the screen. Okay, so what this guy is going to do is, as I mentioned, just blast the pod with HTTP traffic from JMeter. Because I've increased the font size, it's like got these panes on it, and the resolution on this monitor is not doing the interface any justice. But the data in the center is kind of cool, where it'll tell you the different histogram of what the latency data is. You've got what I care about is normally a 95th, 99th percentile. I want to make sure that's reasonable. In this case, about 200 milliseconds. A lot of that cost is because it's in the public cloud. It's on low-powered VMs. When you start running this thing on bare metal, it'll be in the tens of milliseconds range. It's like night and day, performance-wise. So you can tell where I fall in the performance scenario, whether it's public or private, but it's neither here nor there. So this will run for a minute. It's almost done now at this point, 10 seconds. And what I forgot to show you was that there's corresponding load being shown on these thingamajigs, these Grafana graphs. So you can see that there's some CPU usage on the right-hand side, there's some additional memory usage, and most importantly, there's network traffic. In this case, it's about 40 to 50 megabits of HTTP getting blasted at this one pod. And that pod is constrained to only 512 megs of RAM. C groups to do that in the background. These just happens to be a default for the examples that are in OpenShift. So anyway, that's all the data that shows that the test actually occurred on the same system. So that's actually the end of the demo, and probably the end of the talk. So I did forget to ask for questions again. So why don't I just open it up? Who thinks this is useless and no one cares about this sort of thing? Not me. Okay. Who sees something that they can now bring back and use? I'm very happy. I'm very happy you came and you could see that what we're working with. And just remember that all this stuff we're going to get into, some of it is already into the product I had mentioned. More stuff is coming. And so you can expect to see some of this type of stuff bubble into the rest. Like we'd love to shove this thing into cloud forms, right? We don't want to have you off on the side with this graphite thing. We want it formally into a product, a Red Hat product. So I don't really care where it lands myself. At this point in the toy versus tool phase, this works for me as I analyze the cluster. So who's got questions? I will cat my bash history to Twitter. It actually shows that I just can't type. There's another hand. I spun it up myself because Grafana takes a ton of disk space, and I wanted it to persist because actually, I forgot to mention to you, our QE guys have written the world's perfect Jenkins job so that we can set up and tear down clusters on any infrastructure. It's incredible what they've done, phenomenal. And this cluster was spun up using that job, which uses OpenShift Ansible. So there's no secret there other than the fact that we talk to EC2 API in order to set up the nodes themselves. And then we go in and load it up with OpenShift, and then the process occurs like I described to you. We'll probably get as much as we possibly can into the repository that I shared with you earlier. Some of this stuff is kind of tied to our internal process. I don't know if it really makes sense. But we commit everything to that repo anyway. So there are READMEs in there. Part of the handoff between my team and QE is a demo to the QE guys as well as documentation. And that documentation gets committed as a README in that repo. So. I also did a presentation to the Google guys most recently, but it doesn't make sense for Summit. It was a 5-minute thing about our repository. Here nor there, you can go and look at the README in GitHub. Who else? Sir?
The monitoring that the OpenShift Online team is using, we actually use Grafana. We do a lot of the same stuff. Is that the monitors they're pulling out that they feel are useful? Is that something I can reference?
So, I'm glad you asked. I had mentioned that we're trying to learn everything we can from OpenShift.com. Spoiler, we're going to not only productize, but also publish that stuff. Actually, they use Zabbix. So we're talking to Zabbix through Grafana, which there's thankfully someone that already glued those together, and we just sort of use it. But they're more interested in monitoring from an alerting perspective, and I'm interested from a capacity planning perspective. So, but anyway, so that's how that works, and we're going to talk about it a lot more as you see our products come closer and closer to GA for OpenShift Online. So, sir?
Did you do any comparison between different hosts, like real-time hosts versus
Yeah, so RT is still in the experimentation phase, so I'll just leave that at that. But yes, we do bare metal versus VMs, and in fact, I did a presentation at Summit last year specifically on that topic. In fact, I will be doing the same presentation at LinuxCon in August. So if you are in Toronto in August, you will see that presentation revised for containers versus VMs. I forget the title. But it's basically a performance shootout between different infras. Got a public cloud one on there now, et cetera. So. Yes, because I need 10-second intervals, and I need to be able to. So at this point, we really need to get in the bowels of things and be able to have more control than those products are going to get it. And this is sort of like we learn what needs to be done. The Kubernetes guys will tell us what metrics are the most important that we should expose. And so we're still sort of in the investigation phase right there, and so feedback is appreciated. But the point is that we'll get most of this stuff productized as time goes on. So, yes?
Drilling down to a specific node, do you do any of that?
Specific node, what was the last part?
Drilling down to a specific node.
Yeah.
So if you have problems in a node that crashes, you want to see what went on there.
Yeah.
And you're running tens of thousands of these.
Yeah. Yeah, that's a trick, man. Any distributed. So what we're currently doing actually is taking just a select number of nodes and presenting them in the GUI, because we're already at several terabytes of disk space just for the Grafana data. And so it's really just that is our only challenge. We have a lot of ideas about how to just do monitoring of that system, much less so a bad node, we're relying on Kubernetes to detect bad nodes and evict at this point, because those comms are already occurring. Adding additional comms for monitoring needs to be done very carefully with design in mind. So anyway, what we do now is we monitor all of the infra, all of the masters, and then select numbers of the nodes to get a sense of what's going on them. Our team also wrote a utility called pbench, which if you just Google for it, you'll see it, and it's got even more details about monitoring on a single node. So if you just Google that guy, you can run any test wrapped with all of this metrics and understand what a single node is doing at any given point in time. Pretty cool utility. Got some nice graphs with it, sir.
I was at the Sysdig booth earlier today.
Yeah.
They get really, really deep.
Yeah.
Kernel.
Yeah.
All the system calls.
Yeah.
Is there any consideration of integrating what they're doing?
It's way above my pay grade, man. I know those guys and have used, and I love their interface. Like, they're clearly more UI, even though it's ncurses, it's like a little bit more UI friendly than normal performance analysis tools. The challenge with that company is that until they get their code open source, it's only going to be a partner play. You would have to be able to install it on OpenShift. We wouldn't be able to ship it. They have proprietary stuff at this time. Well, it's a kernel module. But my point is just that it's not upstream. Yeah, yeah. And they use DKMS, and so there's some challenges there. But I'm not trying to disparage them because that tool is awesome. And they actually just shipped an on-prem version, so that's cool too. So, who knows how I'm doing on time? I don't know if I'm over. Sorry? Maybe one more question? Sir?
I'm just curious, the solution you put on the screen here is more for the OpenStack monitoring or for OpenShift. OpenShift has a solution on the Gluster.
Yes. Yes. That is per pod monitoring. What this data, it's not OpenStack related. But long story short, this approach takes guidance from a project called Browbeat, which is now an upstream OpenStack project, which does monitoring with Grafana. Our team also built that guy. We just took what makes sense for OpenShift. The monitoring in OpenShift right now is per pod. At this point, I don't need that data yet. So we're using per server, because a lot of stuff we're doing is like, we're starting to saturate the metal, so per pod is not really going to matter to me. I want to know how the system itself is running. Memory usage, like leaks, memory leaks in Kubernetes or whatever else. So we're doing stuff at the node level at this point. Currently. Yes. I expect all this to change. The gentleman over there asked, why is it in cloud forms? It's a work in progress. That's all. So, I believe we're pretty much out of time. But thank you all very much for coming. Oh, one last thing, guys. There's 2 more sessions today. One is at the end of the day, the Shaq and Larry show. After that, there's a performance birds of a feather. They are going to herd 30-plus Red Hat performance and kernel guys or systemd guys into a room and give you guys free beer. 5:45 somewhere on this floor.
Thank you very much. It was very, very helpful.
My pleasure. Good to meet you.
Pleasure to meet you.
I'm Jeremy.